All right, we have one more probability distribution to get through, and it's called the Poisson. The Poisson probability distribution. Again, that's Poisson. The Poisson distribution is another discrete, that's all we've done lately, discrete probability distribution, which means you can count the numbers, which is important because it's often used for describing the behavior of rare events with small probabilities, also mainly for events that happen over intervals. Which is what this is. The Poisson distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval, usually time. The random variable x, same as it always has been, the number of occurrences of an event in an interval. The interval can be time, distance, area, volume, or some similar. Most of ours will be time and distance. The formula is right here. It looks weird when you first look at it, but it really only has a couple of things in it. It has mu, you need your mean, and that exponent right there, I can make that a little bigger for you. The exponent right there is a negative mu. The x is the variable, the number of occurrences. And that's also in the denominator down here, x factorial. E is a number right here you should have learned about in Algebra 2 or pre-calculus or advanced algebra. Mu is just the mean number of occurrences of the event over the interval. So those are some good notes to have right there. You might want to know those for tomorrow. All right, requirements. What you have to be true before you can actually use the Poisson distribution. All right, first of all, the random variable x is the number of occurrences over some interval. So you got to have some sort of interval. The occurrences must be random. The occurrences must be independent. Remember, meaning one occurrence is not affected by a previous occurrence, or one occurrence does not affect the next occurrence. The occurrences must be uniformly distributed over the interval being used. Parameters for Poisson, the mean is mu. The standard deviation is kind of unique. The standard deviation is the square root of mu. That's what makes it kind of neat to use, because the standard deviation is very easy to find. You just take the square root of your mu. There are a few differences between the binomial and Poisson, and here's what you need to know what the differences are. The binomial distribution is affected by the sample size, remember, and the probability, because it's n times p is how you get your mean, or the mu. Whereas the Poisson distribution is affected only by what the mean is, not how big the sample is or what the probability is. In a binomial distribution, the possible values go from 0 of x, or 0, 1, blah, 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 to n, but there's a fixed number. In Poisson, the x values are 0, 1, 2, and there is no upper limit, which means you can have as big a number as you need to for your x. Example. For a recent period of 100 years, there were 530 Atlantic hurricanes. Assume the Poisson distribution is a suitable model. Find mu, the mean number of hurricanes, and b, if p of x is the probability of x hurricanes in a randomly selected year, find p of 2, or exactly 2 hurricanes. I'm going to take the slide to the next one and show you what happened. Mu is just hurricanes per year. So take the number of hurricanes, 530, divided it by how many years, 100 years, and it's 5.3 hurricanes per year. And you can see what's happening. The reason we can use Poisson is because we're doing a time interval, an interval of 100 years. All right, so find a probability that a selected year would, any kind of randomly selected year would have 2 hurricanes. I'm going to use the formula. Mu is 5.3. X is p of x right there, which is 2. E is the same all the time, to the negative mu power, which is negative 5.3, all over x factorial, which is 2 factorial. You can punch that straight in your calculator, and you would get something like, or you would get exactly 0.0701. That's simple. There might even be a way to do that on the calculator easier than that. I don't know. Well, I might know. Right, there are times when you can use Poisson as an approximation to doing a binomial. It's a pretty good way to do it. You can do this when the binomial, you can use it to approximate the binomial distribution when n is very large and p is very small. We have a little rule of thumb, not the range rule of thumb, but just a rule of thumb when you can do that. And that is if your n, which is your number of trials, is over 100. And it's good to do that when your n is so big, because to do a binomial when your n is so large would really be very cumbersome, very difficult to work out. And when your n times p, which is your binomial mean, by the way, if your n times p is less than 10. So you need both of those things to happen in order to use the Poisson as an alternative to doing a binomial. Okay, so if those things are both true, if we test it and our number of trials is bigger than 100 and our n times p is less than 10, we need to find our mu. And the way you find your mu is whatever you got for n times p, which means your mu is obviously going to be less than 10 when you do this as an approximation. Okay, one example of when you would do that. This one says in the main Pick 4 game, you pay 50 cents to select a sequence of 4 digits such as 2, 4, 4, 9. If you play the game once every day, find the probability of winning at least once in a year with 365 days. Okay, so the chance of winning, you should know this by now, is 1 out of 10,000 because you have, you're picking 10 digits, 10 digits, 10 digits. So that's 1,000. Sorry, that's 10,000, and you got a 1 out of 10. You got a 1 chance of winning, so 1 out of 10,000. So we need to find out what our mu is, which is n times p. We're going to play it 365 times. So if you do 365 times 1 over 10,000, you get that. Okay, so here's what we have. Our n is bigger than 365. Our p probability is definitely small, but our mu is less than 10. That's what we need. Our n times p is less than 10, and our n is bigger than 3, much bigger than 100. So let me show you how it works here. Last slide. Because we want the probability of at least 1, we'll find, we always do. Anytime we see at least 1, we always do probability of 0 and do 1 minus probability of 0. So I did that. I put a 0 for my x there and there. Now the weird thing about 0 factorial, it's 1. It looks weird having a 0 in your denominator, but 0 factorial by definition is 1. Negative mu up there, your e here, work it out, I got that. Now don't think that's not your answer. That's probability of 0 and of not winning at all. So the probability of winning at least one time would be 1 minus that. So there is your probability of winning at least one time throughout the year. And that's all there is to it. Again, there might be a quicker way on the calculator. I don't know. I'll have to look. Not really, but I'll see it tomorrow. We'll talk about it. Have a good one. See you then.